Good afternoon, everyone. It's a pleasure to be here and to talk about Fujitsu's approach to quantum computing. So before I go into the talk, I would just like to briefly acknowledge Dr. Shintaro Sato, who was supposed to give this talk before, this Omicron variant actually spread oil sport. So I have to give this talk right now. So this is the roadmap for the computing technology at Fujitsu. So we have been doing cutting-edge computing technology for almost 70 years now. And we have actually created various supercomputers like the K computer or the Fugaku, which I'll talk about. And we can see that as we keep on going further and further, we are reaching the limits of classical computing. So in future, in order to solve these massive amounts of data that we have in today's world, in order to solve problems with that, we need special purpose hardware and also, of course, quantum computing. However, based on the experience that we have over the past 70 years, we are going to push R&D into next generation processors as well as special purpose architectures like the digital annealer, which I'll talk about. So this talk is mainly about quantum computing at Fujitsu. However, we believe that in order to solve all these social problems that we want to tackle, like drug discovery, material discovery, artificial intelligence, and so on, quantum computers need to actually talk with special purpose hardware accelerators as well as classical computers to basically give the full solution. So I'm going to briefly talk about those technologies too, because we think they will be important also in the future. So in the field of high performance computing, the Fugaku computer, which recently actually was ranked the #1 in the world supercomputer rankings. And it has done so for 4 consecutive terms with aggregate computing power of in the order of 400 petaflops. So we understand that these results show that Fugaku has been evaluated and it has sufficient capabilities to solve various social problems as well as AI problems and data utilization issues. We think that in the HPC field, we'll continue to solve a wide range of social issues like this, as well as create various middleware, hardware, and software so that we can actually provide these things as high performance computing as a service to the customer so that they can utilize this technology to solve their various problems. In the field of quantum computing, we work on both quantum-inspired technology as well as real quantum technology. Now, Fujitsu has already commercialized the digital annealer, which is based on quantum-inspired digital circuits, which are used to solve combinatorial optimization problems. In the quantum gate-based system, we worked with partners like RIKEN to cover technologies of different technologies for quantum systems like hardware as well as software. And we want to develop systems based on superconducting qubits as well as other technologies like diamond spin qubits. I will talk about the details of these systems later on. So first, let me go a little bit deeper into quantum-inspired digital annealer. So here is a kind of a chart which shows the different types of quantum and quantum-inspired technologies together. So on the right-hand side, you have the quantum gate systems, and the quantum gate systems are the ones which actually use total quantum gates with superpositions, qubit superpositions of 1s and 0 states. And various companies like IBM, Google, and IonQ, and also other companies over here, they are already working on that technology. Fujitsu also has efforts on that technology. But on the other side, in the Ising machine-based systems, there is this company, D-Wave, which you just talked about in the previous talk. They have a quantum annealer based on this superconducting circuit, which actually they have commercialized. After that, actually, various other companies created classical annealers. So they actually don't do quantum annealing, but they do simulated annealing on classical circuits. And they created digital circuits to actually mimic a quantum annealer. So Fujitsu is one digital annealer created by Fujitsu is one such circuit. Okay, so it has stable operation in room temperature, unlike the quantum computers, and it's available in a traditional rack and server room. So next, I'll talk about the key aspects of the digital annealer as to how we get this speed up. So it's a special purpose architecture. So it has the second generation digital annealer. It has 8,000 qubits, which are connected in a fully connected topology and having a combined resolution of about 64 bits. And the way that it actually gets its speed up is something that I can say is stochastic parallel search. So the digital circuit actually has some built-in tricks to do all these evaluations in parallel, which a general purpose computer cannot do. So that is where about 1000x speed up is possible. And on top of that, we also have some other tricks to actually increase the acceptance probability of the next move to come out of a local minima, which I show on the right. And this actually increases the speed up even further. So using these kind of speed ups, we can use the digital annealer to actually solve real life optimization problems, which comprises of thousands and hundreds of thousands of bits. So this is the technology roadmap of the digital annealer. So I was talking about the second generation digital annealer here, which has 8,000 bits. And we actually commercialized that in 2018. And subsequently, we found out that even 8,000 bits are pretty not enough for solving real life optimization issues. People are running into problems which are 100,000 bits or 1,000,000 bits. And so we actually hit upon a hardware-software hybrid approach, whereby we released the third generation digital annealer in 2019, which can actually handle now 100,000 bits and fully coupled. And there is actually plans going on right now to even scale it up further to 1,000,000 bits or more in the next generation digital annealer. So this is, of course, a classical circuit. So it will have its limitations going forward because of the exponential blow-up of the problem. But I think until full quantum annealers and large qubit quantum annealers are available, this type of circuit can be used as a bridge technology to actually solve real-life quantum problems. So this is a map, like a table, which shows the different comparisons of the different types of digital and quantum annealers available right now. So the quantum annealer from D-Wave right now has about 5,000 qubits, which are not fully connected. There are some limitations. On the other hand, the classical annealers, they are pushing 100,000 qubits or even 1,000,000 qubits bits with some parallelism and hardware software support. And the main thing over here is not the number of bits, which is of course important to solve real life problems, but also the type of constraints that we actually encounter in real life. So in this respect, actually, we have the digital annealer has built-in equality constraints as well as inequality constraints, which are typically encountered in real life problems, and that helps it to solve actually these problems in a much more efficient way. So I'll give you a few examples of what it has done so far. So the first one is very pertinent now in this pandemic situation. It is the I3 drug discovery. So typically, this requires a lot of trial and error and using wet experiments. So we would like to do this kind of trials inside the silicon so that we can do this quickly. So on the right, you can see the solution that we had obtained using the digital annealer as well as the HPC technology from Fujitsu. So what it did was we designed the drug candidate compounds on the computer, and then we estimate the efficacy by predicting the bond strength between target proteins and the potential candidate where it's going to fit. So this development technology actually, what it does repeated iterations to narrow down the amino acid chains which can actually fit into the target site. And the digital annealer could actually do with the HPC things in 12 hours, which would have taken about a couple of months in the laboratory through 8 experiments to narrow down the candidates. So this kind of technology can actually accelerate drug discovery very, very much. We also use a digital annealer in other sectors, like in the finance sector. We have worked with Melco Investment, where we have done the risk and return analysis of portfolios very quickly. And we have also worked in logistics, worked with Toyota Systems to actually make their supply chain more efficient. So basically speed it up by about 2 to 5%. And that may not be a lot, but actually when you are talking about the huge volume like Toyota, 2 to 5% is actually huge. And then the recent one, which is a very interesting one, we actually worked with the German authorities for their seating, to optimize the seating arrangement in their stadiums. So in this pandemic situation, there were some constraints on social distancing between seats and how many people can be put into the stadium, how many audiences. And by using the digital annealer, we could optimize the seating so that they could actually put in more audiences in the stadium and increases their revenue. So these are some examples of how we have used the digital annealer in real-life situations to increase value for their customers. So now finally, I come to the quantum computing part. So in the quantum computing, we believe that the problems that require enormous amount of calculations will be the ones that will be solved by quantum computers. For example, we should know the energy states of materials accurately using quantum mechanics in order to predict properties of new materials. Such precise calculations using quantum mechanics are very difficult through classical computers. So we believe that this is some area where quantum computers can be of help. Also, prediction of prices of financial products is difficult due to the huge number of possibilities that can happen. So quantum computer algorithms have recently been developed and demonstrated to actually do such kind of predictions in a much quicker time. So by simulating complex quantum-based systems, we can also actually discover maybe novel phenomena which were not previously known. So there are some challenges, of course, as people have been talking about for the last 2 days. So first of all, a practical quantum computer requires more than 1 million qubits actually to do something which is worthwhile. So the current number of qubits, as we know, is hovering around 100. And so there will be some time required before we can hit 1 million qubit quantum computers. So in the meantime, people are actually experimenting with these NISQ computers, which are the noisy intermediate scale quantum computers, to see if we can actually get some quantum advantage by using these smaller computers, which are not perfect. Another problem is this problem of errors. So even with greater than 99% fidelity in the gates, as we keep on multiplying, doing operations one after another on these gates, and we have deeper circuits, the errors keep on accumulating. And so we need error mitigation steps actually to reduce the amount of errors that happens in quantum computers. So these are the challenges. So what is Fujitsu's strategy in developing the next scalable large quantum computers? So our strategy over here is that we would like to collaborate with leading research in universities and leading research institutions to develop this rapidly through the process of open innovation. So last year, we started collaboration projects with RIKEN. RIKEN is analogous to Lawrence Livermore National Labs in US, in Japan, and Delft University of Technology in Netherlands, as well as Osaka University in Japan, and also Quantum Benchmarks, which is now Keysight Technologies. So we cover, our strategy is to cover the full stack of the quantum computing framework. So we'll start work on all systems from quantum device integration all the way up to quantum algorithms and quantum applications. And our target would be, again, to utilize these computers to solve problems in the social domain, like materials, drug discovery, finance, and so on. So first, let me go into the collaboration one by one. So we launched a collaboration with RIKEN about 2 years ago to actually develop hardware and software technology to realize quantum computer with as many as 1,000 logical qubits or even more. This year, actually, we launched the RIKEN RQC Fujitsu Collaboration Center with collaboration with Professor Nakamura. So the idea over here is to use artificial atoms, two-level systems for quantized superconducting circuits. So RIKEN and University of Tokyo have strengths in qubit technology, including the control, readout, and the integration of the superconducting qubits. Fujitsu brings to the table strong material, device, circuit, and system technology. So this is the total quantum stack on the left. And for the hardware part, which we are actually collaborating with RIKEN, you can see the work that we are doing. We actually had already created a single qubit using this Josephson junction, where we are using superconducting materials and quantum tunneling to actually create the qubit. On top of that, we have the components for the readout and for the manipulation of the qubits, as well as the low temperature harness for the fridge, which actually controls the whole system. So we are working with RIKEN on these hardware systems. On the software-related topics, we are actually working with Osaka University to implement software technologies on top of that superconducting qubit computer and to develop applications which customers using quantum computer develop at RIKEN. Another thing that we are working on in the hardware part is this diamond spin qubits. So this is a collaboration with TU Delft in Netherlands. So the idea over here is to form a spin qubit by introducing some impurities into the diamond lattice structure. So over here, the impurity is a tin atom. So when you put in a tin atom inside a diamond lattice structure, there is a spin qubit formation, and then this spin qubit can be manipulated using lasers. So the gate operations between distance qubits can be through light, and this can avoid a lot of crosstalk. So these type of qubits actually are much smaller in size, in dimensions, because of than the superconducting qubits. And actually, most of it can be actually obtained at room temperature and doesn't require that absolute zero superconducting fridge that is required in the other technology. So this is mostly in the research phase. It would be great if we can create a scalable quantum computer out of this because of all these inherent advantages. In the software domain, we actually collaborate with Keysight Technologies, of which Professor Emerson already mentioned it a few minutes ago. So the idea over here is to use error mitigation to actually make the results of the quantum gate circuit much better. So there is this technology called randomized compiling, which actually uses various various implementations of the quantum gate circuit to actually reduce the amount of errors from those circuits. So as you can see on the right-hand side, with randomized compiling, even as the number of gates keeps on increasing, the depth of the gates, the error rate still keeps low, whereas without that, we have very high errors. So these kind of technologies will be needed, error mitigation technologies, for scaling up the quantum computer in the future. On the software side, we work with Osaka University, so Dr. Fuji, and the idea over here is to work on various fault-tolerant technologies and error correction technologies that for the output of the quantum computers. So very recently, we established the Fujitsu Quantum Computing Joint Research Division at Osaka University. The objective is to develop error correction algorithms as well as technologies to elevate the performance of this algorithm to a quantum computer for several thousands of qubits. And also to develop the software for computing using these logical qubits so that it can be used finally to scale up to actually solve real-life social problems. So this is actually the hardware and the software. And finally, we are going to collaborate with our customers to actually launch various types of POCs to see how these can actually work in real-life applications. We are not only going to use quantum computers, but also high-speed quantum simulators, which we have developed and which are based on our HPC technology. So this is our quantum computing roadmap. So the long-term challenge of achieving practical quantum computing to solve social problems, that is our final goal. Next year, we are going to release a quantum simulator based on our HPC technology, our cutting-edge, first in the world HPC technology. So that should be able to handle about 40 to 50 qubits. And then in 2023, we are hoping to release our superconducting quantum computer with with about 100 qubits in collaboration with RIKEN. And from there, a couple of years later, maybe we should be able to get to error-corrected quantum computers with hundreds or even thousands of qubits. So that's the roadmap and for quantum computing in Fujitsu. And thank you for your attention. We have time for some questions.
Time for questions. Do we have any questions out there?
Yes.
Research, et cetera.
Q-Star Alliance.
Q-Star Alliance, are they following your lead in doing the Annealer approach exclusively? That's part one. Part two, how transparent are they going to be on some of the efforts in that alliance? Q-Star.
I am not familiar with that. I'll have to take that offline. Yeah.
Any other questions? Okay, if not, Indradeep, thank you.
There is one more question.
Is there one out here still? Okay.
Mike.
Like we have
So how about classical quantum hybrid computation in relation to the technologies that are developing?
Yes, so I think that is fundamental. So basically, we have to have a quantum computer, and then the output has to be processed classically using error correction and stuff like that. And so the whole solution would be a hybrid quantum classical approach to actually get to those final problems that you want to solve. Yeah, and that's why I told you about our supercomputing capabilities, our special purpose architectures, and we want to actually combine all these technologies to give the global solution.
And was there one more question on this side? Yes. Can we get a microphone over here?
I'm curious about diamond spin-based qubit architectures. Why are you interested in this specific qubit type? What are its advantages compared to superconducting qubits? And what's the difference between tin impurities in diamond and V centers in diamonds?
Yeah, so I cannot tell you the last part of it because I'm not a physicist, but the main reason that we are trying to actually look at other hardware technologies is because there are some inherent advantages of using the spin qubit and the lasers. One big advantage is that it's much smaller in dimensions. So the superconducting qubit requires like cooling down to absolute zero to get the superconducting in the copper wires, and that requires a huge fridge. So if you want to make a million qubit system using that kind of technology, the computer that we have will probably be the size of a building. Whereas if you can reduce your qubits in dimensions, then actually you should be able to get a much smaller computer. The other issue is also that of cooling. So it requires huge amounts of energy to cool things down to that level. So if you can achieve the qubit manipulation at room temperature, then that would be very advantageous. However, there are various technical challenges. There are also other issues of this crosstalk that happens between qubits, and basically if you use lasers, then that problem is reduced. So all these advantages are why we are looking also at other computing hardware technology.
We have time for another question. Any more questions?
So yeah, so I mean, it's a little bit of a gray area. So the total number of qubits, if you just look at the total number of qubits, then the digital circuits still are higher than what the quantum annealers can provide, like D-Wave. But I mean, the type of problem that it can solve depends on the problem characteristics itself. So some problems the digital annealer might be able to solve much better. Some maybe the D-Wave can be able to solve better. So it's a little bit of a gray area. But currently, I think that the digital annealer is very competitive. So it can outperform the D-Wave annealer in various situations.
Okay. How about one last round of applause for Indradeep? Thank you so much.